thank you for the invitation again, Alice and Mala. Really happy to see you all and new faces also. So today I'm going to talk about quantitative MRI. Please feel free to interrupt me during the talk. I'm going to go through a couple of technical slides. So if there's questions, please really don't hesitate to interrupt. Okay, so when we talk about quantitative MRI, we often refer to this broad term in opposition to what we call weighted scans. And I guess you are more familiar with weighted MRI in general, because they really gather a large variety of types of images that you are probably using. So from T1 weighted, T2 weighted, flare images, but we could also have proton density weighted, susceptibility weighted, diffusion, perfusion weighted, etc. There is a large number of scans that we can have that are weighted scans. And the characteristics of these weighted scans is that they are qualitative images that will highlight relative differences in signal intensity between tissues. So basically, we are really trying to get good contrast between tissue of interest. For example, in T1 weighted scans, we are trying to get the best gray to white matter contrast, rather than in flare images, we are going to try to see clearly the lesions in the white matter lesions, in the white matter hypotheses compared to the rest of the normal appearing white matter. And these types of images are pretty good in the way that they are very fast to acquire, and they are also very intuitive, meaning that right from the scanner, when you do the acquisition, you can look at the image without any processing, and you can literally see the T1 weighted scan, and it's already meaningful. You can already see atrophy, you can already see maybe tumors or whatever. And they can be sensitive to different kinds of pathology, as I just mentioned, and therefore they can be applied in many different fields. The drawbacks of these types of images is that they are qualitative. And by qualitative, I mean that the value at each voxel is kind of meaningless by their own. They are only meaningful when you compare them to the rest of the values in the brain. So it's really about the contrast and not necessarily the values of the voxel. And this also is the value of the voxel are also dependent on the scanner, on the protocol, and on the parameters. So they can really vary in function of a large variety of parameters. And finally, something that it's important to keep in mind is that these weighted scans can give only limited insights about what is going on in the microstructure of the tissue. So of course, they can be very good at detecting there is a lesion somewhere, but we don't really have information about what is going on in this lesion. Is it inflammation? Is it edema? Is it demyelination or neurodegeneration? We don't really know, okay? And so that is why quantitative MRI comes into play. And QMRI, again, is a very broad term. Not everybody will agree on what we should consider QMRI or not. In the context of this presentation, I will consider that everything that provides a quantitative image that measures physical property of the tissue could be considered as QMRI. So it's pretty broad, and it gathers these empty R1, R2 star maps, which are called relaxation maps that I will describe more later. But we can also think about all the diffusion models that will be able to extract quantitative metrics such as mean diffusivity, FA, or these kind of things. And these types of metrics are somehow more objective and reproducible than what we have with weighted scans, because they are really a property of the tissues themselves and not dependent on the parameters. And therefore, they can be used as standardized biomarker. So for example, you can really compare the value of the voxel in one patient compared to another, and that will be meaningful. That will tell you something about the tissue. And also you can think about saying, like, let's say, I don't know, 700 value for the R1 map starts to become abnormal in the white matter. Like we can really put threshold and saying this, like below this number, it starts, something is going on. And this is something you cannot do with weighted scans. And interestingly, that's maybe the most important part, all these metrics are also reflective of the microstructural tissue information. So each of these metrics will be sensitive to something different. So I'm not going to explain for all of these methods, there's so many of them. But for example, R1 will be mostly sensitive to myelin, R2 star will be mostly sensitive to iron, etc. I will go through another couple of examples later on. The drawbacks of QMRI is that most of the protocols are pretty time-consuming, and also they require post-processing. So from the scanner, directly, you will never have, almost never have, like a R1 map directly or R2 star directly. Like it requires pretty strong processing after the acquisition. And therefore, I consider them a bit less intuitive because you really need to understand what is the model that you're using in order to interpret correctly the biology also. And so for me, in order to use QMRI in general, I always like to go back to really basic knowledge about MRI, because if you do not know what is a T1 weighted scan and how is the signal acquired, it's impossible for you to understand what is a T1 map, what is the difference between T1 weighted versus T1 map. So going back to the beginning, so if you have a patient and you are interested in looking at his brain, let's say here you have a voxel that I represent here. And I'm pretty sure all of you know that the signal in MRI is what we capture is coming from the water, right? So there is water everywhere in the brain. About 80% of the brain is water. But it's not necessarily water that we care about. It's really about these protons. And protons have very interesting property that we can use to make an image. And there's two main properties. One, that the protons will have this intrinsic property that will make them spin. And it's quantum mechanic. I cannot really explain why. I tried to look into it more, but it's really complex. But it's really like a property of protons, of these molecules by themselves. Like you have a mass, you have also a spin. And they also have, because of their positive charge, a tiny magnetization. So they kind of behave like tiny magnets. And each of these magnets will be oriented in different orientation in a normal condition, let's say right now in the room. However, and something I should say also is that, so this tiny magnetization I represent here as these tiny red arrows, so these tiny vectors. And if you think about thousands of thousands of spin in one voxel and you sum them up, because they are randomly oriented, the magnetization that you have if you sum them up would be 0 because they all cancel each other out, okay? But as soon as you put someone inside a scanner, they will feel a very strong magnetic field that we call B0, coming from the feet to the head of the participants. And this B0 field is always on in the machine. You can never turn it out. And this is what we mean when we say, oh, are you working with a 1.5 or 3 Tesla or 7 Tesla? That is B0 field. So it's super, super strong. And so in my example here, if I put the B0 going in the horizontal direction here, basically, as soon as we put the patient, the spins or like the protons will start behaving in a certain way. And basically, they will orient themselves. So there will be some spins that will be oriented in the same orientation as B0, while some will be opposite to B0. And these different states of positioning of the protons is also quantum mechanic. But just to know that basically it requires more energy for the protons to be in the opposite direction rather than being in the same direction. And so because these vectors are, again, in the same magnitude, two opposite protons basically will cancel each other out. And you can think about that in a very large scale. And the thing that I want to highlight is that at the end, you will always have a tiny excess of protons in the same direction as B0, again, because it's easier, okay? So, but the amount of excess is really tiny. So for example, at 1.5 Tesla, if you have 10,000 protons in the opposite direction of B0, you would have 10,006 in the same direction as B0. So it's tiny, but this tiny excess is what makes MRI possible. Without that, no MRI. So it's pretty cool, I think, to keep that in mind. And so now that we have this magnetization in the same orientation as B0, we want to measure it. We want to make an image out of it, right? So the way people do it in general is that we are going to put some kind of antenna, like a receptor, to try to capture the magnetization. The problem in this situation is that M is so tiny compared to B0. So what we will get from the antenna is B0 plus M, which is basically equal to B0. M is so tiny that we cannot measure it, okay? And so in order to measure M, we need to be clever and we need to make it change such as we can actually capture M specifically. And for that, we use this principle, which is called the Larmor precession. It's the only formula I will show you today, don't worry. But basically, it's about the speed or the frequency at which the protons will rotate. And the speed at which they will rotate will depend on the B0 field. So the stronger like the machine and the faster they will spin, okay? And so if we know this frequency that we can calculate, we can do something very interesting, which is called the resonance. So it's another physics property, and it's why we have R in MRI. So it's pretty important to know. So this resonance part is very key to MRI, as we all know it. And so I don't know if some of you are maybe musician, if you know what is a tuning fork. So it's like this tiny thing in metal with a U shape. If you can knock it somewhere, and it will start resonate and give a sound, like a note. Let's say A 440 hertz, which is like the classic A that we use to tune our instruments. So if you knock one, it will start making the noise. If you have another one that is exactly the same tuning fork, like set to be also resonating at the same frequency, and you put it close, you can actually look in YouTube. There is a lot of interesting videos. And you go closer to the one that is resonating, the second one will also start resonating. It's going to transmit the resonance to the other one. You can stop the first one that you knocked, and the second one will still make music. So it's pretty cool. And this is the resonance part. So if it is set at the same frequency, you can kind of transmit the energy to the other one. And if you take another tuning fork, which is meant to do a C, let's say, and you do the same, it will never resonate. Okay, so it's really, if it's exactly the same frequency, you can have this transmission. And so using exactly the same idea, you can think about the fact that we know at which frequency M is rotating. So we can selectively put a pulse that will have exactly the same frequency and will selectively tilt M. So that's what we do in MRI. So we apply another pulse, which is called B1, which is perpendicular to B0, and it's going to make the magnetization go in this other plane, so in this orientation, similar to B1, okay? And when we do that, we can basically put an antenna in the other direction now, remove B1, and we can measure M selectively. I don't know if so far so good, but that's really key, like it's really basic of MRI, any kind of MRI. But you could tell me like it's a very simplistic model, of course. We don't have only water in the brain. So there is other stuff. There is cells, there is, I don't know, axons in general with, let's say, myelin around it. We could also have iron, for example. And less or more water, I mean, you get the idea, like it could be different from one voxel to another. And more specifically, if you compare, let's say, gray matter to white matter, you can easily understand that the composition of the voxel will be completely different. More axons in white matter, or more cellular bodies in the gray matter, etc. And so depending on the place where the protons that we are capturing the information is, they are going to also have different environment. And this environment is going to impact how they behave. And this difference of behavior is what we capture with relaxometry. So relaxometry is really about trying to understand how different tissue react to this experiment, basically, based on how, like what they are surrounded with. So I will discuss that later, but it's just to give you an idea, like this is relaxometry. Another thing that is very interesting and that I will discuss more is what we call susceptibility. And this is about how protons that we capture the signal are impacted by other molecules that can have magnetic property on their own. And the two main molecules that create additional magnetization in the tissue are iron, which is strongly paramagnetic, meaning that they are going to attract the magnetization toward them, and myelin, which will have the opposite effect, but in a very smaller extent. And so if you can measure susceptibility, you can really try to infer about how much iron, how much myelin we have in the brain. And that can be, of course, very important in many applications. So now going into this maybe terms that you heard before, which are a bit hard to understand at first, but it's not really harder than what I just explained before. So we have this longitudinal and transverse relaxation. And so if we go back to the same example that I was showing you before, you just need to know that this longitudinal axis is the axis where we have B0. So basically at the beginning, everything, all the magnetization is along this axis. And perpendicular, where we put B1, it's called the transverse axis. So if you know that, it's really not that much more complicated. So basically, if we do it again, so as soon as we put B1, it's going to flip the magnetization. And now we know that it's called transverse. So it's going to flip it in the transverse plane. So at this specific time, if we look at how this red vector projects to these two axes, we can see that during B1, there is no longitudinal magnetization because it's like on this axis, there is nothing. And there is full, like complete, like 100% magnetization in the transverse plane. Okay, so that's why I'm putting it at 100% here. But as soon as you stop B1, basically the magnetization is going to start going back to their original position because there is only B0 left. So of course they will try to go back to their original states. And that is what we call relaxation. So basically as during this relaxation, so if I put this vector a little bit more up, you can look at the projection in these two axes and you can see that the longitudinal magnetization is growing up while the transverse relaxation is becoming smaller and smaller over time. And we can do that again and again. And basically you obtain these two exponential curves, one growing up for the longitudinal and one going down for the transverse relaxation. And these two phenomena are really the key of what is T1, what is T2, what is T1 weighted, what is T2 weighted scans. So I will explain why just after. But yeah, it's really important to remember just at least the direction of these two effects. So the longitudinal relaxation would be this growth, while the transverse would be a decay. So now that we know that, we can wonder, how do we make a contrast out of it? Like, how do we make an image? So let's say we want to look at white matter versus gray matter, and we want to make a T1 weighted scan, very basic. So the key is that, as I mentioned earlier, because the structure of the tissue is different in the gray and white matter, the protons inside these voxels will have different rates of relaxation. So they will recover, but at different speed. So for example, the white matter will go back to this original state much faster than the gray matter. And just because of this property, which is intrinsic of the tissue, we can make contrast. If it was exactly the same relaxation rate for any kind of tissue, we will have like nothing. We could not see anything. So because of this, we can basically try to define a time at which we have the biggest contrast between gray and white. So let's say I put my time here and I do a screenshot of the image. And you can see that at this time, if we see the magnetization as a grayscale, as how we look images, we will have a different signal intensity for the white matter and for the gray matter. And that is the reason why in T1 weighted scans, a white matter voxel will always be brighter than a gray matter voxel. So it's really about these rates of relaxation. And in the same idea, if we look at a T2 weighted scan, this time we are looking at the transverse relaxation. And we do the same. We try to find a time at which we have good contrast, because of course, if you wait too long, and if I put my screenshots here, there is no contrast. There is no difference between these two. And same if I do it too quickly, too early on. So I need to wait until the right time where I have good contrast. And again, I can do the same. And that is why this time the gray matter voxels will be brighter than the white matter in a T2 weighted scan. So it's really because we are looking at different curves, different effects, okay? So that is for weighted scans. But now, like using exactly the same example of two tissue behaving differently, we can also extract what we call the T1, quantitative T1. And in order to do that, we want to use something that is not changing, no matter what parameters I do, it's going to be a characteristic of the curve and not something else. So we are going to select a time. We are going to find the time at which we have 63% of recovery. And this will be the T1, quantitative T1 value of this purple curve. And this will be the T1 value, so the time at which we have 63% recovery for the gray matter. So it's really this time when we look at it, it's not a question of intensity or in different range. It's about read time. Like time is the scale in this context. And so we will have a shorter time for the T1 of the white matter rather compared to the gray matter. And that is what makes, again, the contrast. And same principle, I'm going to go faster this time. For the T2 map, we do exactly the same. Okay. So just remember that the weighted scans, in the weighted scans, the contrast and the signal intensity are really dependent on the acquisition. Depending on when you do the screenshot, you will have different intensity, different contrast. In the opposite quantitative scans, the contrast and the signal intensity are properties of the tissue, so they cannot vary in theory. But they can a little bit. But in theory, that is the idea behind it. Okay, so last thing, technical, that I want to touch upon is this idea of susceptibility, which is very interesting. So basically, when we talk about susceptibility, we talk about transverse decay. So we go back to exactly the same figures that I was showing you before. So we have this exponential decay right after we stop B1. And I mentioned also earlier that the rotation at which, like the frequency at which the spins are rotating is defined by B0. Here, I was showing you these types of examples before, but in reality, it's a bit more complex because, of course, it's not a 2D thing happening in the brain, it's 3D system. So in reality, we also have this x-axis, right, that I kind of dismissed just for conceptual understanding earlier. But you need to know that because this time we are going to really look from the top and we are only going to look from this XY plane, okay? And so as long as we have B1, basically all the spins, because again, we selected B1 to be specifically in the same frequency as their rotation, so we have them all rotate exactly in phase, meaning that they are all oriented in the same way, so they will rotate, like if two spins, they will rotate, but at the same speed, right? They don't have any angle between them. However, as soon as you stop B1, they will start behaving differently. And that is because, as I mentioned at the very beginning, spins also behave like tiny magnets on their own. So they create tiny magnetization around them. And this magnetization is going to be also impacting the surrounding spins. So it's kind of a complicated mess at this point, but each spin will impact the other. And you can think about the magnetization as additive. So like the more magnetization in total, the more dephasing you will have. So as soon as we stop, we are going to start having what we call this dephasing. So they are all going to randomly go back to different position, but at a specific rate also. So they will start decaying, like dephasing, more and more, okay? And so that is why if we take the net magnetization, so if we take the projection of these vectors on this y-axis, like this blue arrow that I show, like I don't know if it's visible, but this blue arrow is going to start decaying, and that is the transverse decay because of this dephasing. Because at one point, all the protons will like look at different angles, and therefore there is no total magnetization left because they are all pointing in different direction. Okay. But in reality, it's even more complex than that. Because we could have also additional molecules in the brain. There is not just protons. And let's assume we have, forget about this. Let's assume we have iron, like we have some kind of iron deposition somewhere in the brain. And iron is very magnetic. As I mentioned earlier, it's paramagnetic, so it's going to also create very strong magnetization around the molecule of iron. And so this is going to cause even more dephasing in the surrounding protons. So again, it's going to add more magnetization, dephasing. So therefore, it's going to dephase even faster. Like we are going to have this dephasing that will go even faster at this stage. And that is why we have this T2 star decay. So that is the difference between the T2, like quantitative T2 versus quantitative T2 star. So the T2 star is really what we call the effective transverse relaxation, because it's the real one. Like in reality, it's not just pure water. There is also additional component that can affect the magnetization. So the T2 star will always be shorter than T2, because as soon as you have something that is magnetic, it's going to increase the speed of dephasing. And so the difference between, the effect coming from iron is called T2 prime or susceptibility. So this is really the property of iron. It is susceptible, meaning that it creates something outside of the molecule. And there is a relationship, there is another equation actually. So there is this relationship between T2 star, T2 and T2 prime. It's not necessary that you know, but just what I wanted to highlight is that this equation can be also seen like this. So basically R2 star equal 1 over T2 star. And I just mentioned that because sometimes you will see in papers, people talk about T2 star, and some papers, they will talk about R2 star, and you can be confused. We talk about the same phenomenon, but it's just the inverse interpretation that we need to have. So yeah, that's basically it. So what I want you to remember is that any magnetic molecule will cause dephasing, and that is what we call the susceptibility effect. And the T2 star will reflect the spin-spin dephasing, so the impact of one proton to another, plus what any molecule which creates magnetization add on to that. Okay, so that's enough for the technical stuff. So now, like, why do we care? So we care about it because this matrix reflects the tissue property at some level at least. So it has been shown by many people that, for example, the T1 value is inversely proportional to the myelin content. So here you can see that post-mortem, this myelin staining is of course, there is more myelin in the white matter. And you can see that it corresponds with a low T1, so dark T1 in this image. And similarly, the T2 star has been inversely related to iron. So the more iron, the lower the T2 star. But I mentioned also earlier that these two are like what we extract from relaxometry, but there's plenty of QMRI metrics or techniques that you can use. And so people have tried to compare them. So for example, in this meta-analysis, they looked at all the QMRI metrics that people have used to detect or like at least interpret myelin content. And you can see that some metrics are more sensitive to myelin than others. For example, like if you look at the mean R square value, the higher it is, the more correlation we have. So we see that, for example, the myelin water fraction, MTR, QNT, T1 are pretty well showing myelin. However, there is other metrics such as QSM or R2 star that are not that correlated to myelin. Oh my God, I'm confused now. So it's important to know, because if you want to design your study, let's say, and you specifically want to look at myelin, you can look at some papers like that really show proofs of like what is the best correlate that we can obtain from QMRI. Another example for R2 star this time, showing that it is very highly correlated with iron concentration. So here they looked at R2 star in different regions of the brain, different participants, and they also looked at postmortem iron in the tissue. So showing that we can pretty much consider that R2 star is like strongly related to iron. And finally, just 3 applications that I wanted to show. So here we are looking at 2 MS patients. So of course, we can use FLAIR images to look at their white matter lesions, and we can detect them pretty well in these 2 patients. However, it is fairly impossible to know if they are at the same stage of the disease. Like, we don't really know anything from FLAIR. As I mentioned earlier, they are good at detecting, but we cannot really know what is going on inside. So here they also used other QMRI metrics that I didn't touch upon today because it's impossible. But here they are using Chi positive, which is a very good marker of iron. And they demonstrated that this first patient has a pretty large amount of iron in the lesion, as you can see, hopefully, here. And they have this iron rim that we call. So it's like really at the boundaries of the lesion, we can see that it's pretty bright, so lots of iron. However, in this patient down there, like there is no iron at all. And if they looked at Chi negative as well, which is also another QMRI metric that is sensitive to myelin. And of course, they demonstrated that in both lesions, there is demyelination, but that is kind of known already. But this difference of iron is pretty key, because if you think about clinicians, like they want to know, can we do something about it? Can we treat this patient? Can we reverse the lesion somehow? And this, the fact that there is iron here in this lesion, for example, is indicative that this lesion is still active. There is still inflammation going on. So it is probably like at an earlier stage than for this patient, for which there is not even inflammation. It's more like a scar than anything else. So that can really have a clinical impact, I think. Another example in Parkinson's disease, where here they looked at the volume of different regions of interest, so the putamen, caudate nucleus, and pallidum. And so here in the first column, you have the controls, and then you have different Parkinson's disease patients at different stage of the disease, going from very like early diagnosed participants after 1 year of the diagnostic, up to on the right, the more advanced case of Parkinson's disease. And what they demonstrated is that basically the only difference that they found was really between this very advanced Parkinson's disease patient versus the rest of the other participants. So not really sensitive to the first stage of the disease. However, they also looked at R2 star, which is again a marker of iron. And here they demonstrated that even at the very beginning of the disease, they already see an increase of iron. And that can be because, first of all, it is known that iron accumulates in this region, but it can be very interesting to know that we can actually detect this very early on in the disease. We could potentially use it as a biomarker to help the diagnostic, etc. And finally, I could not do a presentation without mentioning what Olivier is doing here. And so I think this is a very cool proof also that it has potential for clinical studies or anything like that. So here, I mean, you probably heard about it more than me recently, but what Olivier did is that he used different QMRI parameters together. And I think that is what makes the big strength of this approach. So he used diffusion metrics, but also susceptibility metrics such as T2 star, QSM. And by combining them all, like he tried to see how the different lesions of the white matter, like how much abnormality we found. And it demonstrated that the lesions that are close to the ventricles do not really show that much abnormality throughout all the metrics that we have. However, in lesions that are deeper in the white matter, we see this very large, for example, increase of MD compared to normal appearing white matter and lower ICVF, etc. So putting together all these metrics, we can start to have some kind of idea of like what is going on in the lesions. And that can be, I think, used in clinical studies, could be also applied in MS, let's say, to see like what is happening in the lesion. And yeah, sorry, I still have something to say. So I just wanted to touch upon quickly the protocol. I mean, of course, depending on what you want to do, there is plenty of protocols. Here, I just wanted to show you what we call MPM protocol, or multi-parametric mapping. So it's a protocol that I'm currently using in my lab. And it's pretty interesting because in one acquisition, you can obtain different maps So you can have R1, R2 star, proton density, and MT. So different metrics that can be pretty useful to combine together to do something like what Olivier is trying to do, like combining different source of information together. And so I'm just going to skip the details, but like basically we are acquiring a bunch of scans, which are all weighted scans at first. And then we are also acquiring the B1 map, B0 map to correct for these inhomogeneities. And then there is this very useful toolbox that is available on GitHub. So basically you input everything and that can provide you these QMRI maps right away. So it's pretty intuitive. And so there is a paper explaining that toolbox from a few years ago now. And there is also an example data set that you can use and test if you want to see how it works. Just know that this toolbox runs on MATLAB. So that's the fun part of it. I'm more used to it now, but it's still a work in progress. But it's very easy to use. Like you basically have this toolbox and you can just input your different scans, different echoes, different maps, blah, blah, blah. And basically you just click and obtain the result. I mean, of course, if you want to go deeper, you can also open each function, each thing. But even for knowledgeable physician, you can use it pretty easily. And ask me question if you want to use that, because I'm using it. And my lab is also like contributors of this toolbox. So just to finish off, I think that QMRI has a lot of potential. We see a pretty large increase of QMRI papers. I believe the decrease at the end is mostly COVID related, we'll see. But I think QMRI will become more and more accessible. If you go to conferences talking about that, for example, ICMRM, like they are really doing amazing work, like physicists per se, like trying to make it more easy to use, faster acquisition, higher resolution. And there's always new metrics coming out, which can be more specific and sensitive to the biology. So I think that is very interesting. And so I think there's a lot of applications in clinics that we can do in the future years. And also I think what is really key is trying to do this multimodal, multimetric types of analysis to really understand what is going on in the tissue. And of course, I could not finish without mentioning this amazing QMRI conference that we organized with Olivier Malard, Christine Tardif, and other researchers the last 2 years. And there is a YouTube channel, very, very cool content in videos, like all the keynote speakers were amazing with different topics each year. And I think if you want to know more about a specific technique, like most likely there is a video about it. So yeah, thank you.